Okay, so today, for this review video, we're going to take a look at mole conversions and when do you use mole conversions in chemistry and what are some of the common ways we do mole conversions. So before we do that, let's review on why this concept of a mole is important. So if you remember back to last year, a mole is a unit of measurement. So much like a dozen means 12, a ream means 500, a gross is 144, or a dozen dozens. A mole is a amount. Okay, so if I say a pair, I'm talking about two things, and we know that, so we know how this works out. But a mole, the thing with a mole is, if you remember back, a mole is it's a massive amount. Well, how much is a mole? It's 6.022 times 10 to the 23rd of something. Items. Theoretically, you could have a mole of anything, but in practical circumstances, most of the time we're talking about moles. Again, we're talking about atoms or particles. Okay. Well, why is it important to making sure that we know this? Well, if we think back to chemistry, so chemistry, you know, if you look at chemistry, it happens on an atom-to-atom basis. And what does that mean? Well, if we look at the smallest form of a chemical reaction, let's say we're going to produce some water. So we got H2 plus O2 goes to H2O. Okay, so if we wanted to balance that, there we go. Now we have a balanced chemical reaction. Well, the simplest form of this reaction, what's going on? I've got two sets of hydrogen molecules. I'm going to draw those over here. So I've got two sets of hydrogen molecules reacting with what? One oxygen molecule. That's not correct. Reacting with one oxygen molecule, and it produces what? It produces two H2O molecules. Okay, so on the smallest scale, if we look at this reaction, this is what's happening, right? And we're actually counting individual atoms here. We have 1, 2, 3, 4. We have 4 hydrogen atoms. Well, we need 1, 2, 3, 4 hydrogen atoms. But we've got 2 oxygen atoms here. Okay? So we want to make sure that there's 2 oxygen atoms on the other side, right? So we got 1, 2, 2 there. Okay? So on the most basic level, chemistry is happening on this atom-to-atom basis. Okay? And if we remember back that, you know, this set of hydrogen right here has a molar mass of, or atomic mass of 2 AMUs. While this set of 2 pairs of oxygen atoms over here, their atomic mass is 32 AMUs. So we can't just weigh them and say, well, if I have 5 grams of hydrogen is equal to 5 grams of oxygen, because that's not true, because on the atomic level they weigh different amounts. Okay? So 5 grams is actually not equal to 5 grams as far as particles are concerned. And since our chemical reactions are actually happening on a particle level of, hey, I need this many of these, I need this many of these, you know, I need 2 hydrogen molecules to react with 1 oxygen molecule to produce 2 water molecules, well, I've got a way to count that. And how do we count that? Well, we count that through moles. Okay, so that's the method that we're doing. And that's why it's so important. You know, if you can't convert to moles, you really can't compare to chemicals. So the biggest thing I'm going to press this year as we're going through chemistry, if nothing else, if you don't know what else to do, first thing you should always do, convert to moles. That's always a great step. Okay? The first thing you should do, if you don't know what to do, is make sure you convert to moles. Okay? That will never be incorrect. Okay, that'll always be a good first step. So first, convert to moles. Well, how do we do that? A couple different ways to convert to moles. We're going to go over 3 today. Okay, so the first one is by using the molar mass. So this is, you know, distinct for each chemical or an element. The molar mass are the grams per mole. So in hydrogen's case, if I have 1 mole of hydrogen, Okay, 1 mole of hydrogen ion or molecules like I had up there. The molar mass would be 1 gram per mole. All right, if we take a different element, let's say we get a helium. Okay, helium. If I have a mole of helium, so I'm talking about 6.022 times 10 to the 23rd atoms of helium, then it would weigh 4 grams. Okay. Or you could say its molar mass is 4 grams per mole. And if you remember right, we find these on the periodic table. Okay, so the atomic mass is the same as the molar mass, the units just change. All right, so what does that do for us? Well, let's do a conversion really quick. So how many moles are present in 15 grams of hydrochloric acid, or HCl? Okay, so let's look at what we got here. This is where dimensional analysis really starts to play a part. Okay, so we've got grams here, and what do I want to go to? I want to go to moles, right? So I want to change my units. So I'm going to start with 15 grams up here. Okay, my railroad tracks ready. Well, if I have grams in the top, I want to cancel out grams in the bottom. And what do I want to go to? Well, I want to go to moles. Okay, so do I have anything that has a unit of grams and moles? Well, yeah. The molar mass, if we just talked about here, what do I've got? I've got grams and I've got a mole amount. Okay, so I know for hydrochloric acid, I know 1 mole, I can find out how much that weighs. Go back. Hydrogen has a molar mass of 1 gram per mole. And chlorine, I'm going to round, and I'm just going to say it has a molar mass of 15 grams per mole. Okay. Or that will equal, since we have 1 of each, we have a molar mass of 36 grams per 1 mole of hydrochloric acid. So I'm going to take that 36 here, put it down here with the gram amount. I'm going to do that. Okay, my grams cancel out. And what am I left with? I'm left with moles, and I've got 0.42 moles of HCl. So, mass to mole. So anytime you deal with masses to moles, or moles to mass, or anything like that, we must use the molar mass from the periodic table. And you've got to use that molar mass. It's the only way to do it. So the most basic way, and the way we're probably most comfortable with from doing last year, how do we go from moles to mass? We've got to use the molar mass and make sure units are lined up. Okay. All right, a second way. Let's look at solutions. Okay, so solutions. You can't just go weigh a solution. Say if I had 10 grams of an HCl solution, I can't use the same method that I just did, because within this 10 grams is some weight or some mass due to the water. So I've got to have a different way to convert from to moles, because again, what's the only way we compare chemicals? The only way we compare chemicals is through moles. Why? Because chemistry happens on this atom-to-atom basis up here. Okay? So, solutions. If we remember back, solutions, we're introducing this new unit called molarity. Okay? And molarity is equal to the number of moles I have per liter. Okay? Moles per liter equals molarity. Always go back to that. Moles over liter. So let's do an example problem real quick. Let's take a look at it. How many moles are present in 10 liters of a 0.5 molar solution of HCl? So let's go back. Well, our units tell us the answer. So if we look up here, if I know molarity in one of these other two values, I can find the other one, right? If I've got 3 variables, if I know one, I can always find the other one out. So let's just set that up. So molarity is equal to moles over liters. Okay, and let's plug in what we know. I have 0.5 molar is equal to X moles divided by 10 liters. Okay, well, can I solve for this? Yeah, I'm going to multiply both sides by 10 liters. The liters cancel out because remember molarity is really moles per liter. Okay, so you could say that's moles over liters, and liters cancel. What am I left with? I'm left with 5 moles. Okay, so for solutions, so we've gone over for mass, we want to use the molar mass. For solutions, we've got to use molarity. Okay, and you've got to have one of these, or you've got to have 2 of those 3 variables in order to solve for solutions. Okay, to get to moles from there. And then the final way I'm going to review right here is for gases. Okay, for gases, we must use the ideal gas law. Okay, so the ideal gas law is PV is equal to nRT. This is the only, no, that's not the only. This is the equation that you have to use if we're solving for moles for gas. Okay, so we've got to have a little bit more stuff, right? We've got some more variables, we've got a constant in here. So we have to have a little bit more information when we're solving for moles of gases. So let's take a look at this. How many moles are present in a 5-liter container or sample of O2 at 10 atm and 273 Kelvin. So if we remember back to ideal gas law, we've got pressure in atm, volume in liters, N is going to be moles, R is my gas constant, 0.0821 liter atm per mole Kelvin, and T is my temperature in Kelvin. Okay, so now we just kind of plug and chug away. So let's see what we got here. At 10 atm, my pressure times my 5 liters is equal to moles, because I don't know that. My constant, I always know, is 0.0821 liter atm per mole Kelvin. And then in this case, my temperature is already converted to Kelvin for me. I've got 273 Kelvin. Kelvin cancel. I'm going to divide both sides by this value. I'm just going to be lazy here and draw an arrow over there and let you know I'm dividing by that. And what I come out to is N is equal to 2.23 moles. Okay, so there's 3 ways to convert to moles. Just a little refresher for you guys, since we haven't, before spring break was quite a while ago, before you've been in school. So moles, why do we use it? And this is critical. If you remember nothing else from this video, we've got to remember this. Hey, chemistry happens on this atom-to-atom basis, and therefore I've got to know how many atoms I have. Okay, if I don't know how many atoms I have, I cannot compare and actually do any equations with them. Okay, so if you don't know what to do in a problem, the first thing you should do, you should always convert to moles. Why? It's the only way to compare chemicals.